properties, the hiding property and the binding property. The hiding property, it means that after the first phase is, or after the commit phase, the adversary should not get or should not learn any information about the committed message. And the binding property, it means that after the commit phase, the person who commits should not be able to reveal a different value than the one that was originally committed. And we talked about two different ways of, or like two different types of these properties. One is like it's hiding in computational sense or unconditional, or the same thing for the binding. And we showed with a very quick proof that a commitment scheme cannot satisfy both properties in unconditional sense. The best we hope for is that it can satisfy one property unconditionally and the other property will be satisfied in computational sense. Of course, you can design a commitment scheme that is very poor and doesn't satisfy any, but since we know that you can achieve one in unconditional and the other in computational, then we always try to design a commitment scheme that satisfies at least one property unconditionally and the other one in computational, depending on which property you are more keen to. So the commitment scheme we're going to, again, you can use hash functions with random numbers to build commitment schemes. This is very similar. Again, if you took 610 with me, you have seen it, like designing protocols with commitment schemes using hash functions and random variables. The only bad thing about it is that there is not that much. Usually we use commitment schemes to build something bigger. So if you use this hash function idea, there is very little you can do with it. So sometimes I would like, actually, when I commit something, I would like to prove something about the value I committed without revealing it. So we can combine the world of commitment schemes with zero knowledge proofs. Usually, if you do this with hash functions, you cannot achieve such primitives. For example, in some situations, I would like to convince you that the value I committed is either a 0 or 1. If you're using hash functions, you cannot do this type of thing. So the commitment scheme I'm going to describe in here is the Pedersen commitment scheme. It's a very famous one because it's used as a primitive in electronic voting. But in this course, I'm actually not going to go into electronic voting. I'm just going to stop at these basic primitives. Maybe we'll just have one fancy protocol that combines several of the primitives we're learning. But the other protocols are actually very difficult to describe in a classroom environment. It will take you forever to explain them, and even if I explain them, I always worry about how I'm going to examine you on them. So if you like to learn more, whatever we're covering in class would allow you to read very advanced cryptographic protocols. But we're not learning very advanced protocols. Learning the small boxes that are concatenated together in this protocol. So this protocol I would like just to commit to a value x. This is what this protocol allows me to. So in here, this is the receiver. And this side is the sender. So the sender here is the person who commits. And this side is the person that receives the commitment. So it chooses P and Q such that Q divides P minus 1. So P and Q are prime numbers and Q divides P minus 1. Then it picks A in ZQ, which means that A is just a number between 1 and Q minus 1. Then it computes H equal to G to the power A mod P. And then it publishes this side. This step should be here. Publish P, Q, G, and H. just a little note to refresh your number theory stuff. If I pick q in this way, then g to the power q is actually congruent to 1 mod p. If q divides p minus 1, then this equation is satisfied. If you don't remember it, just take it as is for now. But again, we have studied this when we took the primitive, like the primitives for number theory. It again follows from Fermat-Little theorem that if you pick q that divides p minus 1, then you have this. So now the sender is going to commit the value x by sending a commitment that is equal to g to the power x, h to the power r, mod p. And in the reveal phase or the opening phase, he is just going to send x. So now we're going to look at the two properties of interest similar to zero knowledge protocols. Every time we looked at zero knowledge protocols, we were looking at 3 properties. Here I only look at 2 of them, but I have to figure out whether each one of them is holding in unconditionally or it's holding in computational sense. So I'm going to prove to you that the hiding property is unconditional. So this commitment scheme is unconditionally hiding. So which means that no matter how powerful the person who is sitting on that side, he cannot find x. So even if he has infinite computational power, he cannot find x. And the idea is always very simple. Since I'm using a random number, the idea is that for every x, there will be another x with another random number that will give me the same commitment. So if this is the case, then you can never find x. If x has a unique solution, then this property cannot hold unconditional. So again, like suppose I would like to design a problem that no one would ever know for sure which value I picked. I will just make sure that the commitment could have been produced by all values equally likely. So for every x and c, I can find another x dash that will give me the same c. Actually, all x's can give me the same c if I change r. So my way of showing that it is unconditionally hiding is that I will show that given c, every value of x is equally likely to produce c. So I'm just going to show you that if I have x, so this is a commitment that is produced by x and r. I'm going to show you this is c, right?
Yes.
I'm going to tell you that I have another x bar and h bar that will give me the same value. So which values of x and r, like how can I find x bar and r bar that would satisfy this? So I already fixed x and r. I'm going to tell you that I can find x bar and r bar that will also produce the same. So just work out the exponents in here. So g to the power x and h is what?
G to a.
So this equation implies what? It implies that this exponent is equal to that exponent, right?
Yes.
But it's equal to it modulo q. This is the only piece that we're sort of like, not all of you may not get the background for it, but just take it for now. Take it as is. It's the main thing is that what we call that the G is the generator and the order of the group is Q. So it means that I have G to the power 1, G to the power 2, G to the power 3, up to G to the power Q will give me 1. So I start with G to the power 0, it's equal to 1. G to the power 1 is G, G to the power 2 is G squared. Until I reach G to the power Q, I'm actually circulating back and I'm getting 1 again. But it's not really very relevant to show these properties. This is just, if I'm trying to formalize my equations, I would say that this implies that x plus AR is equal to x dash plus AR dash, but this equation is actually modulo Q. So this is mod Q. What really matters for me is that I can just pick any x dash and then I can calculate r dash. That will make this equation satisfied. So r dash, how can I find r dash? R dash would equal to x plus AR minus x bar times AM modulo Q. So what I showed here is that if I give you C, you cannot, no matter how powerful you are, you cannot tell which x I use, because every time you pick x, I can always, there is another chance that this C would have been produced by another x, say x bar, for example. And the only difference is that I'm going to pick another random number. So now this is unconditionally hiding, so for the binding property, the best I hope for is that it's going to be computationally binding. My way of doing it, that's a very standard way of doing things. If you like to convince me that this is computationally something, show me that if you are able to break this property, then you would be able to break some problem that we know that it's computationally infeasible to solve. So what I'm going to show to you is that if I am able to break this property, I am able to solve the discrete log problem. So if I'm able to break the binding property, what does it mean? It means that I'm able to change my mind. Right? So basically, I'm going to start with the same equation actually. So it means that I'm able to find x and x bar such that so breaking the binding property, it means that after I send you this, I am able to find x bar and r bar that satisfies this equation. So this is what it means to break this binding property, right? So you can write here, breaking the binding property implies that after committing x, the person will be able to find x bar not equal to x, such that this equation holds. So what does it mean? So this implies that I have g to the power x minus x bar equals to h of r bar minus r, right? So we take the discrete log of both sides to the base g. Just take the log to the base g of both sides. So what would we get?
X minus X.
So x minus x dash equals r dash minus r log of h, right?
Yeah.
So again, who is doing this? Like, who is breaking the binding property?
Alice.
Alice, right? So if Alice is able to break the binding property, I just showed you that Alice can find the discrete log of h, right? But remember that h is not chosen by Alice. H is chosen by that side. H is g to the power a, right? It's picked by that side. It's not picked by Alice. So what I showed you now, if Alice is able to break the binding property, I can use it as an oracle to solve the discrete log problem. I just send her h that she did not choose, and she can return back to me the discrete log of h to the base g. And we know that solving the discrete log is computationally infeasible, which means that the assumption I have here must be wrong, because it's computationally infeasible to solve the discrete log problem. So this is a very standard way of proving the computational. Like, if you like to prove that any, like, suppose you design something and you like to prove that it is computationally secure. Our way of doing it is that you use it as an oracle, like you design an attack against it, and you use this attack as an oracle to solve some mathematically difficult problem. Right? So this is a proof by contradiction, right? So suppose I'm designing a cryptographic protocol, and I would like to prove to you that this protocol is secure in computational sense. So we have seen several protocols in the beginning of the year that were just designed in a very ad hoc way, and they tend to be broken. But one way to design probably secure protocols is to do something similar to this. You design the protocol in such a way that if someone is able to break it, you can use this attacker as an oracle to solve a problem that no one is able to solve. And then this will just be a proof that this attacker doesn't exist. Because if it exists, it means that I am able to solve the discrete log problem, but we know we are not able to solve the discrete log problem. So in here I prove that this scheme is computationally binding, which means that it is secure against, or this property, it cannot be broken by a computationally bounded adversary. Because if it can be broken, it means that I can use this person who is able to break it to solve a discrete log problem. But I know that solving a discrete log problem is computationally infeasible, which means that I must have started with the wrong assumptions. So it's a proof by contradiction, you can think of it this way. And again, this equation is also like, this equation is satisfied modulo Q, but it doesn't make a difference. Any questions on this one? Okay, so can someone summarize to me these two properties, or the proofs of these two properties? You laughed first, so you. Just give it a try, I'm going to help.
Computational binding, we will prove it by contradiction. We are assuming that
let me summarize again, like even if you're not getting the details now, let me summarize to you the high-level picture of any commitment scheme, right? When you are studying any commitment scheme, you need to know how it works. For the exam, I have to give to you how it works. But I can ask you a question that in which you are supposed to answer questions whether they are satisfying the hiding property or the binding property, and in which sense. Right? So how it works is almost trivial, because this is equivalent to showing the completeness in the zero knowledge, right? It just, if I reveal X, I should be able to, I am actually going to reveal X and R, right? If I reveal X and R, I can always verify that C is satisfying this equation. So here I'm going to accept it as the correct opening if it satisfies this equation. So here it should verify that, so suppose I can call it verify that C is equal to these revealed values, right? So when I prove the unconditional hiding, my way of showing that it's unconditional hiding is to show you that there are more than one solution. All x's can be valid solutions. Basically, if I fix x, I can always find x dash not equal to x that will generate the same commitment if I use a different random number. And again, there is very simple formula that I'm using. So this is a commitment. I'm going to show you that there exists another x bar that's not equal to x, another r dash that would give me this equation. And if you have things multiplied together, you add the exponents. And it's nothing more than whatever we were doing in any discrete log-based protocols where we're just multiplying exponents, equating exponents, and so on. In the proving of the computationally binding property, we showed that our proof shows that if you can break the binding property, then you are able to solve the discrete log problem, which means that the assumption we started with is not valid. So in here, in my opening phase, I revealed the x. But in some situations, I actually would like to convince you that I know x without revealing x. So we're going to use something that, this is what? This is zero knowledge, right? So I'm going to have a commitment scheme in which the opening phase is done in zero knowledge. So certainly I can build, like again, we're just talking about primitives, little primitives, but certainly that feature would allow me to achieve something more useful. Because here, once I reveal x, you commit it to x, you reveal the x, you're gone. But if I am able to convince you that I know x, that is a valid opening for the commitment, but I don't want to tell you x.
Excuse me. Computational binding, it is designed because of the other part cannot change the value. This is
so the assumption, no, binding.
Binding.
So always talk about this side and that side, right? So I'm talking. You are the adversary is sitting on that side now, and my assumption is that this adversary is computationally bounded. If he has infinite computational power, he can break this property. Because he can always find x and x bar that would break this property. But if he is computationally bounded, he cannot, because again, I showed you if he is computationally bounded, we know he will not be able to solve the discrete log. But I just showed you if he is able to break this property, then he is able to show the discrete log, which is a contradiction. Again, your best way of making sure you understand it is to try it by hand. If you're just trying to read the slides, that's not a good way to study for these sort of things. To make your life easy in the exam, if I ask you this kind of question, I'm not asking you to memorize these protocols. I will give you the protocol. But you have to be able to do the proofs, and if you practice the proof for the stuff that we cover in class, you'll be able to do it for similar things as well. So now what I'm going to do is that I'm going just to show you the version of the Peterson commitment scheme where the opening phase is done in zero knowledge. So we're not going to reveal X. We're just going to provide a zero knowledge proof that, or Alice, the person that commits, is going to provide a zero knowledge proof that she knows X. So this is the scheme, the original scheme. So this is zero knowledge. So this is Peterson commitment with zero knowledge proof of how to open. So in the original one, the commitment was g to the power x, h to the power r, and the. In this case, you have to make sure that h is chosen by this side, because otherwise, that proof will be useless. If h is chosen by this side can choose x by just picking a random a that it knows and raising g to the power a and.
Oh, we don't understand. What are you talking about?
Okay, that was a. If Siri don't get it.
We don't get it. What are you talking about? That was exactly.
So how many of you is sharing like his views with Siri? So forget about this one for now. Let's stick to this one, the easier version. And if you have any questions about it, ask.
Siri doesn't understand.
What about us?
So again, when we talk about commitment schemes, we're only concerned about two properties: binding a property and the hiding a property. Binding, it means that you don't want the person who commits to change his mind. Hiding, you don't want the other side to be able to tell information about the committed value. If you like to prove something is unconditionally either binding or hiding, your way of doing it is to show that this problem doesn't have a unique solution. So this is an abstract sense, right? And if you like to prove that something is unconditionally whatever property, show that breaking this property implies solving a harder problem. So in our case, since everything was discrete log based, and for this case, we were talking about computationally binding commitment scheme. We showed that breaking the binding property implies solving the discrete log problem. So again, imagine I give you this. So this is what you will be given in the exam. This is given to you. Say this is the commitment phase, this is the opening phase. And then I ask, like, I don't have any questions to ask about this except for asking you either to ask you, does it satisfy this in computational sense or in an unconditional sense? And I can ask you to prove these properties. So if I would like to prove that this commitment scheme is unconditionally hiding, all I have to show you is that there is no unique X that satisfies this. Like there is more, all X's I can satisfy C by just varying R. So it's actually the same equation we use in both. So if you are to prove the unconditionally hiding property, you just show that I have, for every x and r, I have another pair, x dash and r dash, that would satisfy C. Any of you guys is taking the course of Dr. Jeremy Clark, the Bitcoin or blockchain one? So any questions on this commitment scheme? Siri? Before I move, like, okay, good.
For the unconditional finding, why did you apply the mod Q, the modules Q for the when we to prove that there are what is the solution that will create the two use modules Q for the when you put the equation for the C1 C2 x r x prime r prime in an equation when we got the exponents. We had mod Q, not mod P. What's the rationale on that?
This is something we call the order of the group, right? So Q here is the order of the group. So G is the like why we're calling it, we're giving the symbol G because this is the generator of the group. So the way the group is generated is that you have a generator G, and then you raise G to the power 0, you get 1. You raise G to the power 1, you get G. G to the power 2, you get G squared. Up to G to the power Q. So order of the group is the number of elements in the group. So G to the power Q will give you 1 again. So it's as if I have a group, the elements in my group are 1, G, G squared, G cubed, up to G Q minus 1. Mod P, everything is mod P. So why the order of the group is Q minus 1? Because I designed the group in such a way, I picked Q to satisfy that Q is divisible by P minus 1. So this is like number theory stuff, like it's not going to affect anything unless I give you some numbers to work with. But in here, I'm just going to operate with symbols. So it's not going to affect any of these properties. So if I tell you that the order of the group is Q, then I don't have anything in here. It's meaningless to have anything here that's bigger than Q, right? So you can put anything in the exponent. You can actually reduce it modulo. Like the Fermat-Little theorem says, okay, so I can actually, if I am working with, so Fermat-Little theorem, if GCD between X and P is equal to 1, then this would imply that X to the power P minus 1 is 1 mod P. Alright, so you just replace this by Q. Actually, it's better, yes. Okay, keep it back as P. This is P minus 1 and this is 1. So this is one thing you can think of it, right? If I have elements in, so this is one thing that might be useful. But in our case, what I'm saying is that my elements are generated this way, that they are all the elements I'm dealing with are along this circle. 1g to the power 1, g to the power 2, g to the power 3, up to g to the power q minus 1. So what it means that if I give you, if I divide by g to the power q minus 1, it's equivalent to division by what? By 1, right? So it means that in the exponent, I can reduce it modulo q1 minus 1 without changing the result. Right? Maybe actually you don't care about this right now. I think it's enough just to look into this picture. So if I say that if the order of my group is q, it means that in the exponent, whatever numbers I'm dealing with, I can reduce them modulo q minus 1 without changing the result. So I'm actually not going to be dealing with numbers that are larger than q minus 1. So it basically means that if I tell you that x or g to the power a is equal to g to the power b, what you can conclude about this, you cannot say a is equal to b. If this is mod b, right? I cannot say a is equal to b because it might be a is equal to b plus q minus 1, and I still would get the same result, right? So the only thing I can conclude about this would imply that a is congruent to b mod q minus 1, right? Again, assuming that the generator G has an order q. But again, this is just for formality. For proving the properties, we did not really care that much about this. Like,
Well, in the exam, we have to pull out the solution.
yes, but it's very unlikely I'm going to give you numerical questions for this. If I were to ask questions this, I would assume that you're dealing with symbols. It would be good actually to be precise. Actually, since I spent that much time in it, I'm expecting you now to be precise. But anything in the exponent, if you're working with a group generated this way, then it is going to be reduced modulo. Okay, so just to finish this part in which we use this commitment scheme, traditionally the opening phase here would be what? No, I mean, in the original scheme, I just reveal x, right? The opening phase, I reveal x and r.
X and
But if you replace this with the zero knowledge, then it's going to be slightly more like some additional steps. So we're going to pick y and s belong to zq. Then I'm going to send d. Do you expect this to be happening in one step before I go like with this? Like,
No.
so this part is going to be a zero knowledge proof actually. Right? So you would expect that this guy must send some challenge. Right? You cannot just have a zero knowledge proof where this side is just sending everything from. So all zero knowledge proof we have seen have this interaction. So I'm going to send d equal to g to the power y, h to the power s. This guy is sending a challenge, e, and then the reply is u equals y plus ex. And then this guy is going to accept if g to the power u, h to the power v is equal to d c to the power e mod d. And I can ask you actually, what kind of questions I can ask you for this?
The three properties.
The three properties, right? So the first one is trivial because again, you can just show that the left-hand side is equal to the right-hand side. Can you prove the, can you show me the extractor? What is the secret here? X is the secret, right?
X is the
So
secret.
how can I design the extractor very quickly? Like that doesn't need that much thinking.
Fix the same D and choose two different choices.
When you're fixing the same D, it means that because Y and S were random, right? So it means that I'm going to run this one time. Then I'm going to reset this guy, which will force him to pick the same Y and S. But I'm going to challenge him with a different E. Right. So what you're going to get, actually, you're going to get
Two ones.
another U,
And the Y.
right, that is generated by two different E's. And you can just actually subtract the two equations. Y will cancel out, and you will get E1 minus E2 times X. You'll get this value. And you know E1 and E2, so you will just be able to find X. Take this as an exercise. You can do it at home to prove the extractor and the simulator. And that's actually very trivial to do if you understand the rationale behind it. I mean, again, the difficult part is to come up with this protocol, but I'm not asking you to come up with the protocol. I'm giving you the protocol. G to the power U, H to the power V equals D, C to the power E.
What is V?
V is from the original protocol. Actually, no, there's something missing in here. Yeah, okay. So something is missing here. I have the V here. It's actually it just doesn't. I also have V equals S plus ER. But V is not used in the extractor. So what's H in this one? What is H here? Where did we get H from?
This is G2.
So that side is the one that picks H, right?
G to the power L mod P.
So one way to ensure that you are able to solve at least 3-4 questions in the midterm is just to practice these proofs for, it's actually the easiest part of the course because it's extremely systematic. The zero knowledge proofs, I don't have any tricks. I literally told you everything I know. Right? So you talk about 3 properties, the proofs are extremely systematic. I'm going to give you the protocol.
Please give us sample.
Same for the,
Please give us sample.
give you some.
Sample of question.
I don't have samples of questions for this because basically again, the protocol will be given to you and you already have lots of questions among the ones we solved in here. So when you go home, how many things did we cover here? Like how many zero knowledge proofs we covered? We talked about 2 zero knowledge. At counting this one, there will be 3. So we have the one with the Fiat-Shamir, the other one is Schnorr, and this one. And how many commitment schemes did we cover? We only covered 1 commitment scheme, right? So then and I'm telling you, I'm going to ask from this set. Any questions?
Yes, what are some applications combining the commitment with the zero knowledge?
the part I did not explain, and I'm going to skip actually these slides. So if you see the slides, there are a couple of slides, but the way this kind of things, like you can actually push it more. I can prove to you, for example, that what I committed is either a 0 or 1, using very similar things, right? So why why is that useful? Because in electronic voting, I actually going to send my vote, and there will be someone who's going to tally the votes.
Yeah.
But the assumption is my vote is going to be in the exponent. And the way it's going to work is that I don't want to put some value that is going to be count, like it's either a 0 or 1. I don't want to put, like, you don't want to give a candidate 100, for example, right? So I wanted to make sure that whatever value I am committing, I don't want to show it to anyone, but it's going to be tallied. It's going to be somehow, with another protocol, is going to do this secure sum, but he's going to sum the numbers in the exponent, for example, right? So I don't want him to sum, for fairness, I don't want someone to his vote to count as 100, right? So I want you to either vote with 1 or vote with a 0, right? So this is an example for cases where you would like to prove to someone that the value you are committing is either a 0 or 1. Actually, that proof is in the slides, but I'm not going to cover it here. There will be a couple of slides, and I think it's the slide number. Uh, 11, 12, 13, and 14. So I don't think I'm going just for now. If you have set 4, read them because they are very simple. It's actually it's a very good exercise that you do it at home, but it's going to be very tedious to do it on the board here. And it's good because it's going to combine all the primitives we have seen. So slide 11, 12, 13, 14, not going to be part of like. But again, if you're looking for solving examples, that's a nice solving example. Any questions?